In this video, I will be doing 15 vector problems. Two forces act on an object. Force A is 5 newtons to the east, and force B is 7 newtons to the east. What is the net force acting on the object? First, we will identify our variables. Force A is equal to 5 newtons in the direction of east. Force B is equal to 7 newtons, also in the direction of east. And what we're trying to find is the net force acting on the object. The net force is equal to the sum of all forces acting on the object. Since both our objects are going in the same direction, east, the net force will be equal to force A plus force B. Plugging in our variables, we get 5 newtons plus 7 newtons is equal to 12 newtons in the east direction. And this is our final answer for the net force. Two people are pushing a box. One exerts a force of 100 newtons to the west, the other a force of 175 newtons to the west. What is the net force exerted on the box? First, let's identify our variables. Force 1 is equal to 100 newtons to the west. Force 2 is equal to 175 newtons to the west. What we're trying to find is the net force exerted on the box. Net force is equal to the sum of all independent forces acting on our object. As both these forces are going in the same direction, west, our net force is equal to force 1 plus force 2. Subbing in our variables, we get 100 newtons plus 175 newtons is equal to our net force of 275 newtons in the west direction. And this is the net force exerted on the box. An object experiences a force of 10 newtons to the right and another force of 4 newtons to the left. What is the net force on the object? First, let's identify our variables. Force 1 is equal to 10 newtons in the right direction. Force 2 is equal to 4 newtons in the left direction. What we're trying to find is the net force on the object. The net force is equal to the sum of all forces acting on the object. In this example, our forces are going in the opposite directions. Because of that, the net force is actually going to be the difference between the larger and the smaller force acting on the object. Because of this, our equation is that the net force is equal to force 1 minus force 2. Using this formula, we get 10 newtons minus 4 newtons to give us a net force of 6 newtons. And the direction will be to the right, as that was the direction that the larger force was moving in. Two soccer players kick a ball simultaneously from opposite sides. Player 1 kicks with 50 newtons of force, while player 2 kicks with 63 newtons of force. What is the net force on the ball? First, let's identify our variables. Force 1 will be equal to player 1's kick, which was 50 newtons of force. Force 2 will equal to player 2's kick, which was 63 newtons of force. What we're trying to find is the net force acting on the ball. The net force is equal to the sum of all forces acting on the ball. Because the ball was kicked simultaneously from opposite sides, our forces are going in opposite directions. Our net force is equal to the difference between the large and the small force acting on the object. Using this formula, our net force will be equal to F2 minus F1. Plugging in, we get 63 newtons minus 50 newtons for a net force of 13 newtons. And the direction will be in the direction of the larger object, which is the direction of the second player's kick. Vector A is 7 units to the north, vector b is 3 units to the north. What is the result of a minus b? First, let's identify our variables. Vector a is equal to 7 units to the north. Vector b is equal to 3 units to the north. What we're trying to find is the result of a minus b. Subtracting a vector is the same as saying adding the negative of the vector. Because vector b is now negative, it has the same magnitude of 3 units, but is in the opposite direction of north, which is south. Now we can subtract the two vectors to get 7 units minus 3 units is equal to 4 units, and the direction will be north as that is the direction of the larger vector. A person walks 3 meters north and then 4 meters east. What is their resultant displacement? The easiest way to work this problem is to visualize it using a graph. We can put north on the y-axis and east on the x-axis. If a person walks 3 meters north and then 4 meters east, that will leave them somewhere out here. This forms a right triangle where the northward movement is one leg, the eastward movement is another leg, and the resultant displacement is the hypotenuse. Now we're able to calculate the magnitude of the displacement by using Pythagorean's theorem of a squared plus b squared is equal to c squared. A can represent the first movement, which was 3 meters north, and b can represent the second movement of 4 meters west. Now plugging in our variables, we get 3 squared plus 4 squared is equal to our displacement c squared. 3 squared is equal to 3 times 3, which is 9, and 4 squared is equal to 4 times 4, which is 16. 9 plus 16 is equal to our displacement squared, and 9 plus 16 is 25. To get rid of the square in our displacement, we must square root both sides. The square root of 25 is 5, and that is equal to the magnitude of our displacement, c. In order to find the direction of the displacement, we're going to find this angle, theta, right here. In order to find this angle, we will use the trig identity of tangent of theta is equal to the opposite over the adjacent legs. Using this, theta is equal to the inverse tangent of the opposite over adjacent legs. For this, our opposite leg is equal to 3, and our adjacent leg is equal to 4. Plugging in, we find that theta is equal to tangent inverse of 3 over 4. Plugging into the calculator, theta is equal to 36.87 degrees. Putting this all together, our final displacement has a magnitude of 5 meters in the direction of 36.87 degrees north of east. Force P has a magnitude of 6 newtons and acts along the positive x-axis. Force Q has a magnitude of 8 newtons and acts along the positive y-axis. Find the magnitude and direction of the resultant force. The easiest way to visualize this problem is by graphing it. Our first force, force P, has a magnitude of 6 newtons and acts along the positive x-axis. Our second force, Q, has a magnitude of 8 newtons and acts along the positive y-axis. These two forces form the legs of a right triangle where the displacement is equal to our hypotenuse. Now we can use Pythagorean's theorem of a squared plus b squared is equal to c squared in order to find our displacement. A can be force P, which has a magnitude of 6 newtons, and B can be force Q, which has a magnitude of 8 newtons. Plugging into our formula, we have 6 squared plus 8 squared is equal to our displacement c squared. 6 squared is equal to 6 times 6, which is equal to 36. 8 squared is equal to 8 times 8, which is equal to 64. 36 plus 64 is equal to our displacement squared. 36 plus 64 is equal to 100, And in order to get rid of the square on our displacement, we must square root both sides. The square root of 100 is 10, and that is the magnitude of our displacement. In order to find the direction of the resultant force, we need to find this angle theta. To find theta, we can use the trig function of tangent of theta is equal to the opposite over adjacent legs. And theta is equal to tangent inverse of the opposite over adjacent legs. Our opposite leg is equal to force Q, which is equal to 8, and our adjacent leg is equal to force P, which is equal to 6. Plugging into the formula, we get that theta is equal to the inverse tangent of 8 over 6. Then plugging into the calculator, we get theta is equal to 53.13 degrees. Our final answer is that the resultant force has a magnitude of 10 newtons and is 53.13 degrees from the x-axis, or north of east. A bird flies with a velocity of 3 meters per second east and experiences a crosswind with a velocity of 4 meters per second north. What is the bird's resultant velocity? The easiest way to visualize this is by graphing it. Our bird flies with a velocity of 3 meters per second east and experiences a crosswind with a velocity of 4 meters per second north. In order to find the bird's resultant velocity, we can form a right triangle using the velocities of the bird and the crosswind, where the resultant velocity is equal to the hypotenuse. In order to find the resultant velocity, we'll use Pythagorean's theorem of a squared plus b squared is equal to c squared. A can be the velocity of the bird, A can be equal to the velocity of the bird, which is 3, and B can be equal to the velocity of the crosswind, which is 4. Plugging into our equation, we get 3 squared plus 4 squared is equal to c squared. 3 squared is equal to 3 times 3, which is equal to 9, and 4 squared is equal to 4 times 4, which is equal to 16. 9 plus 16 is equal to our resultant velocity squared. 9 plus 16 is 25, and in order to get rid of the square on our resultant velocity, we must square root both sides. The square root of 25 is equal to 5, and that is equal to the magnitude of our resultant velocity. In order to find the direction of the resultant velocity, we need to find this angle theta. In order to find theta, we will use the trig function that tangent of theta is equal to the opposite over adjacent legs. And theta is equal to inverse tangent of the opposite over adjacent legs. Our opposite leg is equal to the direction of the crosswind, which is 4, and our adjacent leg is equal to the bird's flight velocity, which is 3. So theta is equal to the inverse tangent of 4 over 3. Plugging this into the calculator, we get that theta is equal to 53.13 degrees. Our final answer is that the resultant velocity of the bird has a magnitude of 5 meters per second and is 53.13 degrees from the x-axis, or north of east. You walk 5 meters along a street and then turn a corner and walk another 12 meters perpendicular to your initial direction. What is your total displacement? The easiest way to visualize this problem is to graph it. Let's say the first 5 meters that you walked were in the y direction. Then you turned perpendicular, which is equal to 90 degrees from your initial direction. That can mean that you either went along the negative or positive x-axis. For this example, we're going to say that you went down the positive x-axis another 12 meters. In order to find the total displacement, you can form a right triangle with the distances that you walked as the legs, and your hypotenuse is equal to the total displacement. To find the displacement, we can use Pythagorean's theorem of a squared plus b squared is equal to c squared. We can say that a is equal to our first walk of 5 meters, and b is equal to our second walk of 12 meters. Plugging into our equation, we get 5 squared plus 12 squared is equal to our displacement c squared. 5 squared is equal to 5 times 5, which is equal to 25. 12 squared is equal to 12 times 12, which is equal to 144. 25 plus 144 is equal to our displacement of c squared. 25 plus 144 is equal to 169. In order to get rid of the square on our displacement, we must square root both sides of the equation. The square root of 169 is 13, and that is equal to the magnitude of our displacement. Our final answer for the total displacement is 13 meters, and there is no direction as our initial direction is unknown. Force A has a magnitude of 5 newtons and acts at an angle of 0 degrees from the positive x-axis. Force B has a magnitude of 4 newtons and acts at an angle of 90 degrees from the positive x-axis. What is the resultant force? The easiest way to visualize this problem is to graph it. Our first force, force A, had a magnitude of 5 newtons, 0 degrees from the positive x-axis. That means that it is just along the positive x-axis. Force B has a magnitude of 4 newtons and acts at an angle of 90 degrees from the positive x-axis. This means that it is along the positive y-axis. In order to find the resultant force, we can form a right triangle with forces A and B as the legs, and the magnitude of the resultant force will be the hypotenuse. In order to find the magnitude, we can use Pythagorean's equation of a squared plus b squared is equal to c squared. A can be equal to force A, which is 5 newtons, and B can be equal to force B, which is 4 newtons. Plugging into the equation, we get 5 squared plus 4 squared is equal to the magnitude of our resultant force c squared. 5 squared is equal to 5 times 5, which is equal to 25, and 4 squared is equal to 4 times 4, which is equal to 16. 25 plus 16 is equal to c squared. 25 plus 16 is equal to 41. And in order to get rid of this square, we must square root both sides. Plugging into the calculator, the square root of 41 is approximately 6.4. And this is equal to the magnitude of our resultant force. In order to find the direction of our resultant force, we have to find this angle, theta. In order to find theta, we'll use the trig function tangent of theta is equal to opposite over adjacent legs. Then theta is equal to the inverse tangent of our opposite and adjacent legs. Our opposite leg is equal to force B, which is 4 newtons, and our adjacent leg is equal to force A, which is equal to 5 newtons. Plugging in, we get that theta is equal to tangent inverse of 4 over 5. And using our calculator, theta is equal to 53.13 degrees. Our final answer for the resultant force is that it has a magnitude of 6.4 newtons and is 53.13 degrees from the x-axis. A boat travels 6 kilometers west and then turns and travels 8 kilometers south. What is the boat's total displacement from its starting point? The best way to visualize this problem is to graph it. Our boat first travels 6 kilometers west. Then it travels 8 kilometers south. In order to find the displacement from the starting point, we can form a right triangle using its movements to the south and west as the legs, and our displacement will be equal to the hypotenuse. In order to find the displacement, we can use Pythagorean's theorem of a squared plus b squared is equal to c squared. A can be equal to our travel west, which is 6 kilometers, and b can be equal to our travel south, which is 8 kilometers. Plugging in, we get 6 squared plus 8 squared is equal to the magnitude of our displacement c squared. 6 squared is equal to 6 times 6, which is 36, and 8 squared is equal to 8 times 8, which is equal to 64. 36 plus 64 is equal to the magnitude of our displacement squared. 36 plus 64 is equal to 100, and in order to get rid of the square on our c, we have to square root both sides. The square root of 100 is 10, and that is equal to the magnitude of our displacement. In order to find the direction of our displacement, we need to find this angle, theta. In order to do this, we can use the trig function tangent of theta is equal to the opposite over adjacent legs. And theta is equal to tangent inverse of the opposite over adjacent legs. Our opposite leg is equal to our travel south of 8 kilometers, and our adjacent leg is equal to our travel west of 6 kilometers. Plugging in, we get that theta is equal to the tangent inverse of 8 over 6. And plugging into the calculator, we get that theta is equal to 53.13 degrees. And this will be from the negative x-axis. The final answer for the boat's total displacement is that it has a magnitude of 10 kilometers and is 53.13 degrees from the negative x-axis. A car travels 20 kilometers north and then 15 kilometers west. What is the magnitude of its total displacement from the starting point? The easiest way to visualize this is to graph it. The car first travels 20 kilometers north and then 15 kilometers to the west. In order to find the magnitude of the displacement, we can form a right triangle with the movements north and west as the legs, and our displacement is equal to the hypotenuse. To find the hypotenuse, we can use Pythagorean's theorem of a squared plus b squared is equal to c squared. We can set a equal to our first movement of 20 kilometers north and b equal to our second movement of 15 kilometers west. Plugging into the equation, we get 20 squared plus 15 squared is equal to the magnitude of our displacement c squared. 20 squared is equal to 20 times 20, which is equal to 400, and 15 squared is equal to 15 times 15, which is equal to 225. 400 plus 225 is equal to the magnitude of our displacement squared. 400 plus 225 is equal to 625. And in order to get rid of the square on our c, we must square root both sides. The square root of 625 is just 25, and that is equal to the magnitude of our displacement. So our final answer is that the magnitude of the total displacement is equal to 25 kilometers. A drone flies 100 meters at an angle of 315 degrees measured counterclockwise from the positive x-axis. What are the east and north components of its displacement? In order to visualize the problem, we'll graph it. 315 degrees from the positive x-axis wraps it all the way around, and the drone will be flying in this direction. In order to find the east and north components of its displacement, we can form a right triangle with its flight. The east component of the displacement is equal to the x component, and this can be found by multiplying the magnitude of the displacement by cosine of theta. The north component is equal to the y component of the displacement and can be found by multiplying the magnitude of the displacement times sine of theta. We know that they are cosine sine because we are measuring relative to the positive x-axis. If this was relative to the y-axis, they would be flipped. Now plugging into the equations, our east component dx is equal to 100 times cosine of our angle theta 315 degrees. And this is equal to 70.7 meters. Our north component, dy, is equal to 100 times sine of our angle theta, which is 315 degrees, and is equal to a negative 70.7 meters. Here it makes sense that the north component is negative because it's actually flying south in the negative y direction. So our final answer is that the east component is equal to 70.7 meters, and the north component is equal to a negative 70.7 meters. Two forces act on an object. Force 1 has a magnitude of 10 newtons and acts at an angle of 30 degrees above the positive x-axis. Force 2 has a magnitude of 15 newtons and acts along the positive y-axis. Find the magnitude and direction of the resultant force. The first thing we're going to do is graph the problem. Our force 1 has a magnitude of 10 newtons and acts at an angle of 30 degrees above the positive x-axis. This means that the force is moving somewhere in this direction. We'll pretend that this is 30 degrees. Force 2 has a magnitude of 15 newtons and acts along the positive y-axis. So it is moving somewhere over here. The resultant force will then be somewhere out in this direction. In order to find the magnitude of the resultant force, we will have to break the force up into its x and y components. To do this, we have to find the x and y components of each individual force. Force 1's x component is equal to the magnitude of force 1 times cosine of 30 degrees. And force 1's y component is equal to the magnitude of force 1 times sine of 30 degrees. We know that they are cosine and sine because we are doing this relative to the positive x-axis. Plugging into the equation, we get 10 newtons times cosine of 30 degrees. This gives us 8.66 newtons. For force 1's y, we get 10 newtons times sine of 30 degrees, which gives us 5 newtons. The x component of force 2 is equal to 0. This is because it only moves in the positive y-axis and has no movement in the x-axis. And the y component of force 2 is equal to the magnitude, which is 15 newtons. Now we need to find the resultant x component, which is equal to the sum of the x components of forces 1 and 2. This is equal to 8.66 plus 0, or just 8.66 newtons. The resultant y component is equal to the sum of the two y components of the forces. This is equal to 5 plus 15, which is equal to 20 newtons. And the magnitude of the resultant force is equal to the square root of the sum of the x and y components of the resultant force squared. Plugging in, we get the square root of 8.66 squared plus 20 squared. And this gives us 21.794 newtons. Now to find the direction of the resultant force, we will use the trig function tangent of theta is equal to the opposite over adjacent legs. And theta is equal to the inverse tangent of the opposite and adjacent legs. The opposite leg will be equal to the y component of the resultant force, and the adjacent leg will be equal to the x component of the adjacent force. Now we can plug in to find that theta is equal to the inverse tangent of 20 over 8.66. Plugging into the calculator, we get that theta is equal to 66.57 degrees. And our final answer is that the resultant force has a magnitude of 21.79 newtons and is 66.57 degrees from the positive x-axis. An airplane is flying at a velocity of 200 kilometers an hour due east. It encounters a crosswind blowing at 50 kilometers an hour from the south. This is meaning that the wind is blowing north. What is the resultant velocity of the airplane relative to the ground? The best way to visualize this problem is to graph it. The airplane is flying with a velocity of 200 kilometers an hour due east. Then it is going along the x-axis. The crosswind is blowing at 50 kilometers an hour from the south, meaning that the wind is blowing north. Then it is going along the positive y-axis. And the resultant velocity of the airplane will be somewhere out here. In order to find the resultant velocity of the airplane, we must find the x and y components of the velocity of the airplane and the wind. The x velocity of the airplane is equal to the magnitude of its velocity, 200 kilometers an hour, as it is going directly along the x-axis. The y velocity of the airplane is equal to 0, as it has no movement in the y-axis. The x component of the wind's velocity is equal to 0, as it does not move in the x direction, while the y component of the wind's velocity is equal to 50 kilometers an hour. The x component of the resultant velocity is equal to the sum of the x components of the wind in the airplane. This gives us 200 plus 0, or just 200 kilometers an hour. The y component of the velocity is equal to the sum of the airplane and the wind's y components. This gives us 0 plus 50, or just 50 kilometers an hour. The velocity of the resultant component can be found by taking the square root of the sum of the x and y components squared. This gives us the square root of 200 squared plus 50 squared. This equals 206.16 kilometers per hour. To find the direction of the resultant velocity, we'll use the trig function tangent of theta is equal to the opposite over adjacent legs, and theta is equal to the inverse tangent of the opposite over adjacent legs. Our opposite leg is equal to the y component of the velocity, and our adjacent leg is equal to the x component. Plugging in, we get that theta is equal to the inverse tangent of 50 over 200, which equals 14.04 degrees. So our final answer is that the resultant velocity of the airplane relative to the ground has a magnitude of 206.16 kilometers an hour and is 14.04 degrees relative to the positive x-axis. If you found this video helpful, don't forget to leave a like, subscribe, and let me know in the comments what topics you'd like to see next. Thanks for watching.